Thank you, Matthias. And my name is David Bessnan. I'm a product line manager at Telebyte for the industrial Ethernet test products. And welcome today to our digital coffee break. We're going to discuss the challenges of 10-base T1L single pair Ethernet physical layer testing. So just a brief background on Telebyte. Telebyte has been designing and developing test equipment since the mid-1980s. So we've been in business over 30 years. We're headquartered in a town called Hauppauge, New York, on Long Island. And Telebyte's expertise is really in the design and test industry on physical layer test equipment. So we make cable emulators, noise generators, signal analyzers, and hardware and software test automation, measuring currents, voltages, transmission line theory, signal to noise ratio, noise. That's really the background of Telebyte's engineering team and technical folks. And we're focused on the industrial Ethernet market, including the advanced physical layer for intrinsically safe applications. The agenda today, we have about an hour to spend with you discussing this topic. We're going to introduce single pair Ethernet, and we're going to talk about the current standards of physical layer testing as they apply to 10-base T1L. We're going to look at different types of testing, and then the challenges of the physical layer testing on 10-base T1L. And we're going to wrap up is how to best meet these challenges. And then we can end with a question and answer period. So if you do have questions, please send them over and we'd be happy to answer questions at the end of the presentation. So to start, why is single pair Ethernet, especially 10-base T1L, a game changer? Well, you're taking a ubiquitous technology like Ethernet and you're combining it with DC power so that you have an end-to-end network to power the remote sensors or field devices and bring them onto the enterprise network or cloud. So if you look at the picture here, it kind of looks like any picture you might have seen all the time. You have an Ethernet switch, and then you have devices that connect to the Ethernet switch. That's just kind of a normal layer 2 networking protocol Ethernet with equipment attached. However, if you look closely here, these equipment on the end of the ports, this is, instead of an 8-pair Ethernet wire, it's only a 2-pair or 1-pair Ethernet wire with 2 wires. And so that will provide 10 megabits per second, and it will remotely power the end device. So there's no need to have an electrician out to wire up an auxiliary electrical outlet to power these devices. You could have devices in buildings such as web cameras. For restricted areas, you could have door locks or security. You could have motion detection to turn lights on or monitor safety equipment like smoke alarms or carbon monoxide detectors, or you could be monitoring a process plant with sensors and actuators. You could have heating and HVAC, heating, ventilation, air conditioning controls. You could be controlling conveyor belts or robots or manufacturing. It could be on railroad cars for transportation. So the applications that you could support over an Ethernet network with higher level software applications is really what the Internet of Things and Industry 4.0 is to drive. So what we're doing then over this 2-wire technology, 1 pair with data and power, we're increasing the data rate from the legacy 2-wire devices from kilobits per second up to 10 megabits per second. And that's full duplex, so transmit and receive simultaneously. And we're also supporting power over the same pair from 500 milliwatts low power to high power, 52 watts. So with the low and high power classes, we can support a wide variety of devices on the network. And then the Ethernet advanced physical layer brings in intrinsically safe environments. So if you have flammable gases, hydrogen, or flammable liquids, and there's an explosive environment, then you have to be very careful with low voltage and low current so that you can operate in a hazardous environment. Then what else makes this the advantages of single pair Ethernet is the ease of installation. So having only a single pair cable, it can be shielded or unshielded according to general operational environments. It's only 2 wires, it's smaller, it's lighter, it has a tighter bend radius, so you can fit more cables in a smaller space. So this is advantageous, again, for applications in robotics or transportation where space is limited to run cabling. You can also scale this when you add, just adding another port to the switch, you can scale this up if you need additional equipment on the network. If it's a time-critical application, you can implement time-sensitive networks to provide low latency and prioritization to the Ethernet data. This allows you to ensure that if you're monitoring speed of something or monitoring something quickly, that traffic gets to the controller in a timely manner. So this, when you wrap this up, it provides much more critical data to the controlling and monitoring systems, and with artificial intelligence and pattern recognition, it allows you to keep the operational technology network up and running with less unplanned downtime. The standards that we wanted to discuss, there are multiple standards, but today we're going to focus on 5 standards that we're using for the implementation of physical layer testing on 10-base T1L. So we have the IEEE 802.3 CG standard that was passed in 2019. This defines all the physical layer specifications, operation and management for 10-base T1L. It defines the protocols, the registers, the state machines, the test modes, the operating modes, the power classes, the polarity. It really defines a complete overview and management of the single pair Ethernet. So it discusses a 1 volt peak-to-peak operating mode and also a 2.4 volt peak-to-peak operating mode. These modes are useful over different operating environments and different cable types and lengths. So we'll talk more about that in our testing. Then there's also the IEEE preliminary 802.3 DD standard. This is an update for the power over data line. So they're updating and adding to some of the information that's defined in the CG spec. And this, one of the examples here for 10-base T1L is they're trying to cost reduce some of the devices and reducing the size of some of the inductors in the power coupling circuitry. So they're changing the droop standard here. So they're updating that right now. Then if we look, we have the Ethernet Advanced Physical Layer for intrinsically safe testing and also non-intrinsically safe environments. But they have a number of specifications that you can follow for testing. We're going to focus on 4 right here. There's the port profile specification, and this defines power classes, and especially for deployment of equipment and on an APL certified network, you have trunk lines that can be long lines up to 1,000 meters, or spurs that can be up to 200 meters that you're running the remote devices on. And spurs are defined to operate in a 1 volt peak-to-peak operating mode, and trunks can be higher voltage, the 2.4 volt peak-to-peak mode. They also define data tests and power tests, and then there's engineering guidelines for best practices and for installation and deployment of the equipment. Then we have 2 other standards here, the IEC 61156-13 and also the TIA 568.5 standards. These define other additional cable models and components used for 10-base T1L. So if we look at these 5 standards, they define a lot of the information for how we're going to accomplish our physical layer testing. The first type of testing we're going to discuss is conformance testing. So we have transmitter and receiver validation test. So if you think about it, for Ethernet, the main accomplish, or the main thing your goal is to receive error-free traffic. So in order to do this, we have to transmit the data and we have to receive the data. So if we look here on the receive side, we have receiver validation. We want to make sure that we can receive the traffic error-free, but we also want to do it in a non-ideal condition. So we want to add some noise to reduce the signal-to-noise margin. So we're adding an additive white Gaussian noise at minus 106 dBm per hertz, and that's a flat noise over a 10 megahertz bandwidth or a 20 megahertz bandwidth. So you're raising the noise floor of the cable environment. Then with power over data line, we also may have power line ripple noise. So we're adding low frequency ripple noise from 1 kilohertz to 1 megahertz. And that basically is simulating an environment that you might see on the single pair cable. Then we're using different cable lengths. We could test over 200 meters for a spur, or we could test long cable lengths up to 1,000 meters or beyond, actually, for trunk connections. And we're looking then to keep the SNR, even with this noise condition, better than 20 dB. And so we want to make sure that our bit error rate is very low so that we get error-free traffic. So we're going to pass Ethernet or even upper layer traffic, layer 3 IP traffic, or layer 4 with the TCP protocol or UDP protocols when we test this. Or we can also start using time-sensitive networking and start using timestamps and other prioritization testing. Then we have our transmitter validation test. So this is on the transmit side, there's 3 different test modes. If you think about the transmit signal, we have to make sure that our clock frequency and our timing is within a certain threshold. We have to make sure that our transmitted signal has the right voltage amplitude and the rise and fall times are correct. So we test basically test mode 1 does timing jitter and the output voltage level and tests the clock frequency and a short-term variation of the clock. Then we test in test mode 2 the transmit signal for transmitter output voltage droop. This is where you're sending maybe a pattern of ones or negative ones or zeros, and make sure that the voltage droop isn't exceeding its limits. And then we also do a distortion test, which looks at the unbalance or balance of the transmitted signal. In test mode 3, we test the power spectral density and the output power level that's transmitted. And then finally, we have a MDI, a medium dependent interface return loss measurement, where we want to see how closely the devices match the 100 ohm differential characteristic impedance. So the cable is 100 ohms. We're trying to match for maximum power transfer the impedance of the devices together. So the input impedance matches the output impedance of the devices. So we have to test these in both 1 volt and 2.4 volt peak-to-peak modes, and use different data sequences with a differential high impedance probe and either an oscilloscope or a digitizer to monitor the transmit signals. This is a picture showing some of the transmitter testing. So in test mode 1, we're just going to send a pattern of +1s and -1s continuously. So if you look at the left picture here, we have a 1 volt peak-to-peak signal, and it's just going +1 to -1, and we're just going to send that continuously. And then we're going to capture this signal and then use jitter analysis software to produce an eye diagram. So here in the eye diagram, we can see the signal amplitude level, and we can measure the amplitude and the horizontal opening of the eye. So we have a big eye diagram here, meaning that we have a nice clean signal. We should be able to send data error-free. So if this eye gets closed in the middle, you'll see more errors. We measure the clock frequency. It should be around 7.5 megahertz. And then we're also measuring peak-to-peak jitter, which has to be less than 10 nanoseconds for the clock. So for the 1 volt mode, this is an example of some of the transmitter test mode 1 testing. Then we put the device into a 2.4 volt peak-to-peak mode. So you can see now the voltage swing is higher, 2.4 volts from the peak to the minimum. And then we also do jitter on this test mode. So again, we measure the signal amplitudes and look at the clock frequency of the symbol rate and look at the peak-to-peak jitter. We can provide a histogram then of your results, and of course you have to put the devices, the PHY chipset, into the test mode 1, setting the proper registers. So this is all defined in the standards that we just previously discussed, and we kind of follow that as the method of procedure. You will need a high impedance probe and the digitizer or digital oscilloscope to do this test. In test mode 2, we transmit 10 ones followed by 10 minus ones, and we repeat that pattern to measure the transmitter output voltage droop, and also we can mix in a distortion signal to see what the balance is of the signal. So as I mentioned, the 802.3DD spec is going to reduce the size of the inductors, which reduces the cost of the device, and we're going to increase the droop spec from 10% to 25%. So again, we put the device into test mode 2 with the proper register settings, and now we're looking at a signal here with a 1 volt peak to peak mode, and you'll see now we're transmitting 10 ones, and then we transmit 10 negative ones, and then 10 ones, 10 negative ones. And what we're doing then is measuring this droop here on this signal. So we start from the 0 crossing, and we actually look at 133 nanoseconds later, and we measure this voltage, and then we go from the 0 crossing to 800 nanoseconds, and we measure that timing, and that droop must be less than 25%. And we do the same thing on the negative ones. Then here's a picture showing the 2.4 volt mode. Again, we have the 10 ones and the 10 negative ones, and we measure this droop. Now, with the distortion test, since we have power on the same data pair, there's power coupling and voltage limiting circuits combined on this pair, and you may get what we don't want it to cause is a DC unbalance. So there's data encoding on the 10 base T1L signal to try to minimize any DC bias. So we mix in a 1 megahertz sine wave at 1 volt for the, or 2.4 volts depending on your operating mode. You want to make sure that then we look over time, 10 milliseconds, and make sure that these peaks are the same value of the minus peaks within 50 millivolts. So that's the test that we run in test mode 2. In test mode 3, we basically test the power spectral density and the output power level of the devices. And our test mode 3 signal is actually a normal transmission mode, but we're in idle frames or idle mode. So here's a picture of the time domain signal. This is a 2.4 volt peak operating mode, and you can see the signal is using a 3-level pulse amplitude modulated signal. So we have 0 levels, +1, then we have -1. So that's PAM3 signaling. You might hear it called ternary symbols, since there's a +1 value, a 0 value, and then a -1 value. And in the physical layer, the encoding and decoding of this data into code groups, they take +1, 0, and -1 patterns and turn those into digital data when they do their encoding and decoding. But here, what we want to look at then is we do a fast Fourier transform on the time domain, and we look at the frequency domain signal. So here's a signal in the 2.4 volt operating mode in blue here, and we want to make sure that the power does not go above this upper red limit in a 2.4 volt mode, and then the green bar is the lower limit. So the transmitted signal must be between those two lines. Then we integrate the area under this curve to get the transmitted output power level. We do the same thing again. The black signal here is the 1 volt peak to peak mode. So you can see the 2.4 volt transmit mode has higher power. So you should be able to send signals over longer cables with higher power. And then we also have a 1 volt peak to peak mode for shorter cable lengths where you want to limit the current and the voltage for safe applications. Again, we're using the same equipment for these 3 test modes, test mode 1, 2, and 3. And again, here we're showing writing registers to set it up in test mode 3. The final test we run here in the conformance testing is the MDI return loss. So this is looking at how close the front end of the device is to 100 ohms. So we need a vector network analyzer, and we have to calibrate our cables, but we have a return loss from the standards here in red, and then we measured, we put the device into a high impedance mode and slave mode. So it's not, the transmitter is disabled. And then we look at the characteristic impedance using S11 parameters from the vector network analyzer. And we see here that this device at 10^2 is passing the return loss. So it's a very good 100 ohm characteristic on this device. This is important for error-free data transmission. You want to make sure that you're trying to closely match the impedance as much as possible. The next type of testing we're moving to is the physical coding sublayer. So this is also a physical layer test. But 10^2 I mentioned, I showed you the PAM3 signal, and it's transmitting data at 7.5 megabaud, which gives you 10 megabits per second. But we have to scramble and descramble the data to improve our electromagnetic compatibility when we're sending this data over the cable. And we try to reduce any DC bias. We're trying to have a balanced signal with no DC bias. So the physical coding sublayer does all this mapping and scrambling of data to basically take digital data that goes up to the medium independent interface to what we were just looking at, kind of analog signaling, PAM3 signaling that goes out over the cable. So if we look at the PCS, the physical coding sublayer, we want to test the transmit side from the digital data down to the cable. Then we also want to test the receive side from the cable up to the digital data. So you'll see that we have a transmit test and then receive tests. So we're encoding the digital data into analog data down here. And we look at the ternary signals. There's some encoding with start of stream delimiters, end of stream delimiters, in addition to the Ethernet preamble in the frame. And this information is tested in a training mode, an idle mode, and also data transmission modes. So we need to have arbitrary packet generation and capture of those packets, and also look at use an oscilloscope or digitizer to look at the analog signals. So we do encoding of the data and then decoding on the receive side. When the data's come in, we have to do error handling or any jabber or overruns. Then we have to descramble the data into our digital data. So we want to make sure that we can handle end of stream delimiter errors, disparity errors, or bad status while receiving valid packets. There also is a signal polarity, so we have to handle polarity inversion if required. Then the third type of test here is testing the auto negotiation layer of the physical layer, and that would be with half duplex differential Manchester encoding. So when we go into auto negotiation, there's two devices on the link, right? It's a point-to-point connection. They have to advertise their capabilities, and then they have to negotiate common capabilities between them. So we test the auto negotiation features of restart of negotiation, test link status, fail. If we do fail an auto negotiation, we have to wait so long and then retry again. We also look at the differential Manchester encoding voltage amplitudes. So this is all part of the physical layer testing here. Layer 1, we have our single pair copper cable with the differential pair bidirectional data positive and bidirectional data negative. And we go into the medium dependent interface. Then we have our auto negotiation. Then we have our physical medium attachment layer. Then we have our physical coding sublayer that does all our encoding and decoding of data. Then we have our medium independent interface data where we start getting digital data, ones and zeros. And there's a nibble here for the transmit data and 4 bits here for the receive data. And we might have some Reed-Solomon error encoding CRC addition. Then we get to our MAC layer, our layer 2 MAC data. So not only do we have to test that the transmit and receiver signals are correct here, we also want to look at the encoding here to make sure that we can test that so that it's working correctly so that we can get error-free traffic all the way up to the upper layers. The next topic is actually power class testing. So we've looked at the data side now. Now we want to make sure that the power is stable. So we have to deliver DC power over the single pair. And the 802.3cg standard from the IEEE body has defined for type E devices for 10-base T1L 5 classes. So you have class 10 through 15. But if we look at class 10 through 12 first, you'll see that the voltage power supply on the power source equipment is between 20 to 30 volts. So let's just say typically about 24 volts being supplied from the power source side. And you'll see then that we have maximum cable DC resistance. So we have high DC resistance, 65 ohms, 25 ohms, and 9.5 ohms. So this is a longer cable. And then you, for 24 volts, you put out 92 milliamps, and you can deliver 1.23 watts to the end device that's being powered. So that's relatively low power, and it's at the end device you have a minimum of 14 volts. So if we look at 18 gauge American wire gauge cable in a 2.4 peak-to-peak model, we can see we have about 1,000 meters here. And that's basically what the standard says. You can test out to 1,000 meters. Now you will see that based on the DC resistance of 65 ohms, you could actually test out to 1,400 meters. So a lot of the 5 vendors, Analog Devices and Texas Instruments, will report 10-base T1L beyond the 1,000 meter standard. So we have class 10 through 12. You can see that you can produce higher power, but the cable length gets shorter. So you have some loss in the cable. And of course, the higher power is delivered over shorter cables to the end device. Then we go to class 13 through 15, and you see the voltage increases from 50 to 58 volts. So say typically 55 volts. And again, we have longer cables delivering 7.7 watts. 20 watts and 52 watts over shorter cables for the class 13 through 15. Then if we look at the Ethernet advanced physical layer, they've defined their own power classes and ports as well. So they have class A and C as their safe low voltage classes. You can see their voltage range between 9.6 and 15 volts for class A, and 11.61 volts and 15 volts for class C. So maybe typical 12 volt voltage supplied, and they're running over short cable lengths, 200 meters, providing 500 milliwatts or 1 watt to the end devices. And then they have class 3 for their longer cable runs for trunks. They're using a 2.4 volt peak-to-peak model here when they transmit over trunks, and they can deliver up to 36 watts to the end device. So if you look at these power classes defined, they can support a wide variety of devices on the network. So when we test this too, we have to make sure that since we're delivering voltage and current, if somebody were to short the twisted pair cable, the differential pair together, it should result in a fast voltage turnoff. So if you short the positive and the minus conductors, you should turn the power off within 75 milliseconds. So there are some safety testing that goes on to test this, as well as error registers should be reported from the device if there's power faults. And there's a whole mix of testing going on too, with the slew rates and over current limits and under voltage current limits, and we test all of this is defined in the standard, but really so much detail that we too much to discuss in today's talk. Here's some of the tests we do run, however, though. So we have the power device detection. So if you think about it, you have a field switch delivering power to the end over its ports to the end device. It has to identify the device when it's connected on the end of the cable. So for general purpose single pair power over Ethernet operation, there is a protocol called the Serial Classification Communication Protocol. And that basically lets the PSC talk to the PD and determine what type of power it requires to operate. Then in the advanced physical layer, they have what they call engineered power. So it's already predetermined by the design of the network what the power class will be and what the power delivery will be. It's hard-coded, hardwired, or the device can only deliver what it's going to deliver. It does have to find out, though, if the PD is on the cable or not. So there is a voltage detection signature that is used to turn the power on when the device is connected to the link. So we want to make sure that full voltage isn't applied until you have the power device load connected. And then once the power device is removed, voltage should turn off. And we look at the power class currents. So you saw the low current ranges and the high current ranges, power class voltages. There's low power standby modes. Some of the devices will measure the cable DC resistance. Then we want to make sure that we're using the correct terminal or connector for the application, using there's shielding options to tie the shield directly to earth ground or to capacitively couple to earth ground. We want to test short circuit behavior, and then also the polarity of the power can, for 10 base T1L, it should be insensitive. So whether you have plus minus or minus plus polarity on your DC voltage, we should be able to handle both. We also look at measuring some of the electrical characteristics on the data pair for ripple noise, slew rates of voltage and current, and fault conditions. So this is a picture. You have your 10 base T1L phi, and then you usually have your power coupling. You have a source, a voltage source here, voltage supply and current, and we're sending current and voltage over the same twisted pair and then receiving that power over the pair and powering up this device, all with the same two-wire cable that has data and power on it. So once we know that we can send data, and once we know we can power up the devices correctly, then we want to do interoperability testing. So we want to test a vendor device with other vendors' devices to ensure that they interoperate correctly. So there's some functional tests that we want to run. We want to run the devices in their required operating modes for how they're going to be deployed in the network. We have to test out a negotiation or for force modes. We have to test over variable cable lengths, short cable lengths and longer cable lengths, maybe with different power classes if it's a field switch. We have to test that the PD detection is working. We want to test over worst case cable models. We want to test the cable diagnostics of the devices if they can measure the quality of the cable. We want to test with noise, so we can add noise interference. When we add noise to the cable pair, there's a value called the mean squared error that comes from the 10 base T1L phis, and you can calculate the signal to noise ratio from that. So if you test in non-ideal conditions and lower the SNR, you can make sure that you have data-free or error-free data communication. We want to test again with shorts and full duplex traffic. So what this graph here on the right is showing is bit error rate versus signal to noise ratio. So you can see the bit error rate is quite high if the signal to noise ratio is low, and if the signal noise ratio is high here over greater than 24, you have very low bit error rates, 1e to the minus 22. So this table here is giving you kind of a sense of the link quality, the cable link quality. If you have very good link quality, the SNR is greater than 20.5 dB, and this associates to a hex value that you're reading from the phis in the MSE register, then you'll get a very low bit error rate. So that means you can pass traffic without any errors. Now, as cabling ages and degrades. Once you first deploy the network, everything's, you go through your acceptance testing, you get very low error rates. But over time, that's exposed to harsh environments, weather, temperature, vibration, sometimes different noise environments. You can basically watch this signal to noise ratio and have an idea of when you may need to do maintenance on the network. So as your SNR goes down to say 20.5 or between 19.5 and 20.5, you have marginal bit error rates. Now you're going to see higher number of errors on that link. And then of course, if it gets below 19.5, you have poor margin. So this is a good measure from the device to see if you're going to start having errors on the data traffic. And in the performance and stability tests, we want to test kind of in varying noise environments. So if there is what we call impulsive noise or repetitive electrical impulse noise, this is noise that comes from electrical equipment that's plugged into the electrical outlets, and it radiates impulsive noise. So there's variable frequency drive motors often in plants, there's elevators, there's pulse width modulated energy efficient devices, there's arc welders, there's robotics, that can all generate impulsive noise. And if your shielding isn't installed correctly, that noise can couple into the single pair. So there are some tests that we can do over time and on either unshielded twisted pair or to test how well the data performance is going to be. We can also test alien crosstalk. So if you're using unshielded twisted pair, which 802.3cg says you may do, you could have alien crosstalk from other cables in your cable tray. So you can test if other 10-base T1L devices are coupling in their signals into your cable, the victim cable, you can test with alien crosstalk. But basically we do some longer term time and temperature testing to make sure that the devices are working correctly, so that you know that the devices, once deployed, will work correctly over time. One of the other items here is just to, with the field switches, to fully load the field switch so that you're supplying power to all the ports, and then you can do some of the testing to make sure that you have error-free traffic as well. So, and if you unplug a device, to make sure that any instability on one line doesn't transfer to another port on the switch. And we're doing fault testing where we're unplugging equipment or shorting some of the wires to shield or shorting the differential pair, just to test what may happen in the field. So those are the definitions of tests. So there's quite a thorough amount of tests to make sure that the equipment is working correctly and it's in the standards. But when you start to think about how am I going to test this, my colleague drew this, and it kind of blows your mind here. You have multiple test cases, multiple use cases. There's multiple measurements to make, and you need multiple test instruments, and it's all with power over the same pair as the data. So you want to test the devices, kind of how they're going to be used. So you'd like to include the power and the data together when you're testing. So you have to control the device under test in multiple operating modes and test modes, and you can do that either via Ethernet, the serial parallel interface, or the serial UART connection. You have to have the right version of software from the vendor to be able to put the device into all of these test modes or operating modes. Then if you look at it, the standard 802.3cg calls out 14 gauge wire up to 26 gauge wire. So the 14 gauge wire is very large diameter wire, and the 26 gauge is smaller diameter. And then you have lengths, short lengths to long lengths, 1,000 meters, or even with 14 gauge, maybe up to 2,000 meters. So if you want to test the devices, in your lab, you're going to need quite a few different cables and lengths to test against. Then we have low ranges and high ranges for power, current, and voltage. So again, our equipment has to support a wide range of voltage and current values. And we also want to test with noise. So again, we have low level noise down to 1 kilohertz all the way up to 20 megahertz bandwidth of noise for additive white Gaussian noise, alien crosstalk, impulse noise, or power line ripple. And then how do we set all these pieces of equipment up with our terminations, our test adapters, our test fixtures, the ballons, the clamping circuits, power splitters, programmable loads or power supplies? How do we set this up and then run a test and then run another test and try to make it repeatable from one site to another? It's quite a challenge to do all of this. We are doing physical layer testing, but we also need to pass traffic because we want to pass traffic either with time-sensitive networking or just standard traffic to make sure that we have low bit error rates. So the challenges, it can be quite labor intensive, setting up your test beds with all the test fixtures and couplers and cables. And it's not a trivial thing because you don't want to damage your expensive test instruments either. So you want to make sure you do this correctly and in a safe manner, and that you have good test results. You have to trim multiple cables, single pair cables. You want to match return loss, insertion loss, the group delay. You want to have different DC resistance and different cable lengths. And then you also need multiple test instruments to gather. So you might gather equipment that you have on the lab shelf, either noise generators, function generators, arbitrary waveform generators. You need a high impedance noise injector to put that noise onto the line, or you need coupling circuits. You need oscilloscopes or vector network analyzers, digital multimeters. So again, it includes a wide variety of equipment to connect to the link. And then the cost of testing. So the cost can include money, and it also includes time and resources. So you requires skilled engineers or technicians to run this test. Manual testing is time consuming. You can wear out connectors and other things that cause problems and errors in the test result. You might try to automate this, but that also takes some time to control these multiple instruments and to control the devices and get everything so that you're synced up in time and you're running everything correctly at the right time. And then repeatability is very difficult. So if I'm running this manual test and I'm setting the oscilloscope with rise and fall time triggers, and I'm using a certain ballon or coupling circuit, and I get a test result and I see an issue, if I try to go back to the chipset vendor or another supplier, they might not be able to reproduce that problem, and it might be based because something might be due to my setup. So it is nice to try to have something repeatable from site to site and from company to company. And this can take up quite a bit of laboratory space with the setup. You can rack and stack some of the equipment and you'll need some of the cable spools, but it does take up some space. So how do we meet these challenges? The good news is we can use a fully integrated approach. So first of all, we have to try to follow the standards. We have to follow the standards because they define how to do the testing and what the pass and fail results are. So if we're non-compliant to the standard, then we're not going to be repeatable. So we do have to follow the standards and their method of procedure and their guidelines. So the standards that we discussed earlier, the 802.3CG, the 802.3DD, the Ethernet Advanced Physical Layer, and the cable models, we want to make sure that we're following these standards when we're setting up our test bed. We'll try to integrate as much functionality into the equipment as possible. So if an instrument could measure current or voltage and we can use that in multiple tests, then we need to try to implement that. We try to remove variability and use calibrated test setups whenever testing, so that you have valid test results. And then, if as much as possible, nice to automate this so that there isn't any test that's user dependent that may be hard to reproduce with another person or at another site. And we'd like to try to compact that and do our data and power testing with a setup sort of where we don't change the setup as much as possible. So the fully integrated approach, a universal test setup, this is Telebyte's approach to doing this. What we're doing is taking test instruments and integrating functionality into them. So we have our power source equipment here, and we have a channel emulator. So this channel emulator will support variable cable length types and segment lengths from short lengths to long lengths. It varies the DC resistance from 1 ohm to 80.5 ohms. And you can introduce cable faults, measure current and voltage on each side of the link, and calculate power. We have internal noise generators for AWGN and power line ripple noise in the box. And we can also analyze the classification protocol, the serial communication classification protocol. So the PSC device talks to the PD device. We can monitor that communication, where the PSC determines what power the PD needs. Then we have a high impedance differential probe on this end. We're testing, in this example, we're testing the power device, and we can capture the transmit receive signals from this device. We can also, if the device we take the device out and terminate, we can capture the noise on the cable. So if there's a noise in a setup, we can capture noise. It supports all classes for power for the 802.3cg and advanced physical layer, and it also includes the distortion injector. So what we're doing is having with one setup, trying to universally run all the tests that we've discussed today, from conformance testing to power testing to interoperability testing between devices. This is a setup that may work. So we add some external instruments in here. We might have a VNA here. And then we have our PC, which has an arbitrary waveform generator, digitizer with MATLAB software to do the signal analysis and the jitter analysis. Then we have a traffic generator and protocol generator analyzer. You could use Wireshark or iPerf or some other programs to generate traffic, or you could have an external traffic generator. And then you could try to use test automation software to automate the testing, talking to the multiple devices under test, and also controlling the test instruments. So this is an approach that it makes it easier to accomplish the full list of physical layer testing. And this shows you a cable wiring diagram where we have the digitizer going to the probe, and the probe is capturing the signals here. And then we have an AWG to generate the impulsive noise that we may measure from industrial environments. Then we have our cable emulator here that we're varying trunk or spur cable lengths, so we can test over different cable lengths, different DC resistance. We can introduce cable faults. Then we can also monitor the SNR of the devices and make sure that they're working correctly and reporting the correct signal to noise margin. So this environment helps you measure the voltage and current, reproduce industrial environment, noise environments, and fully automate some test control and reporting for the physical layer testing. The PC also you may load some virtual machines on here and have some Linux machines running data rate with iPerf or other programs, other types of traffic generators you can have controlled as well, or other external equipment. Then the last test we're going to talk about is moving to the system level. So we've tested that devices talk from port to port. Now we want to have kind of a system level test just to make sure it's going to work as how it's going to be deployed in the field. And we have a power switch here coming over a trunk. So this power switch is auxiliary powered, and it's providing power over a single pair trunk. We can monitor the signals coming out of that trunk at the end of it. And then we can go into the field switch, and the field switch is providing power out to the power devices over 8 ports. So we have 5 ports here that are going over 200 meters, and we're injecting some noise on one device here, and we're looking for stable, error-free data on all of these 5 ports. Then we're also going into an intrinsically safe environment where we're using class A or C type testing in this environment where it's an explosive area. So we want to make sure that this field switch and the power devices are working correctly in the system level now. Once we have the field switch and the power switch and the control here going out to the network, the control system and the configuration management system and other even cloud-based systems that are capturing data here for this application. So with this, we can reproduce several different environments when we're testing. So the goal of automation is to try to take the user dependence out of the testing. So if I become very knowledgeable and I can run all the oscilloscopes and all the equipment, but I'm tuning the knobs and running the test so I get the right result, we want to basically, for the success of 10-base T1L, we want to make sure that the testing can be market-wide and that customers have confidence in deploying this technology. So we'd like to try to automate the control of the test setup, the devices under test and the test equipment as much as possible, so that you have a test that's repeatable from your company's lab to another company's lab across the world. So this is just some examples of what the test automation software should control: traffic generators, cable lengths, DC resistance, measuring the device registers, controlling the noise generator, the oscilloscope, the power supplies or the loads, programmable loads, any VNAs or digital multimeters, and storing the data in a database, and then time correlating this, and time correlating really the control of the entire test bed, so that you can run these different tests and get very accurate results and pass and fail test reports with log files. So this is kind of the goal of how to make this testing meet the challenges of this physical layer testing. This is an example of a test automation software report. So this is looking at the power spectral density, which we showed you earlier. And basically this test was automated in the Telebyte lab, and we just run this test. It talks to the device under test, and then it outputs a report here for the 1 volt mode and the 2.4 volt peak to peak mode. Checks this signal that it's not violating mass in an automated software check, and then test the output power against the standard limits. So this is very nice when you click the button and this runs, and then you get the report, and the user can actually focus on the equipment rather than focus on running the test. So you can do test result analysis versus pulling your hair out running the test. That's the end of my discussion. So I think we do have some time for questions.
Yes, we do have some time. We are close to an hour, but I guess we get so many interesting questions already, and so we should use the time to get it. I see. I see one interesting simple question: why use a cable emulator instead of the real cable? So the first answer I can give, because I had an interesting story when we ordered the first time a 1 kilometer drum for Profibus cable to measure it in our lab, and if this arrives, it was a huge amount of cable, and my colleagues from the lab was not very happy to get it. This is the first reason, because real cables are very heavy and big for the 1 kilometer standard. But I guess you have some more answers here for us.
Sure. Yeah. Thank you for the question, Matthias. Yeah, the cable spools can take up quite a bit of space, and then you have to manually connect them or disconnect them, or try to put a switch in to automate connecting cables, and you have to make sure the switch has very low insertion loss and doesn't affect your test results. But Telebyte, that's one of Telebyte's expertise, is making the cable emulators. So a cable emulator, first of all, produces repeatable results from site to site. So if you have different cable spools from site to site, you may actually have different results, because depending on who manufactures the cable, and that there's some variability in 2 1,000 meter lengths of cable. But the cable emulator follows the standards for the 802.3CG and APL and the IEC 61156-13 and the TIA 568.5 cable model. So we follow that standard. So when you measure DC resistance and the insertion loss, you'll get the same results on the cable emulator that you would get on the real cable. And we also can, you can run power over that. So our cable emulator is a transmission line theory, but we designed it so that you can put the high power, the power source equipment can be up over 90 watts, so about 90 watts of power into the cable emulator, and you'll still get very accurate results for the cable losses. But what it also allows us to do is we've integrated features into the cable emulator, such as the current and voltage monitor on each side of the cable. And we've integrated the internal noise generation for the additive white Gaussian noise and the ripple noise. So we can create the same environment on the cable that you will see, from the live deployment of the equipment. So you can do testing in the lab that validates that your equipment is working correctly.
Yeah. Very interesting. I get here one more question, really from the chat. How good are these cables, cable line emulators? Yeah, and the second question, how much they cost? But I guess the second question we can answer in a direct contact. But they ask for the accuracy of the emulators.
The accuracy, well, there's some different specs. So the cable emulator models the insertion loss, the return loss, the group delay, and the characteristic impedance of the cable model. So we follow the 802.3CG standard and the IEC and the TIA standards. So our mean absolute error for insertion loss is like less than 1 dB. So we follow very tight accuracy limits, and we follow the return loss measurements and the group delay, for the standard cable models. The Ethernet APL also defines a worst case spur and trunk. So we follow basically all the standards, and then usually have an error, mean absolute error of less than 1 dB for insertion loss, and we're better return loss, and we follow the group delay that are defined in the standard. So they are very accurate for the standard cable. Yes, for the standard base models.
Yeah, another question I see or come up, especially if we go to the process industry with APL and so on, there is also a huge number of installed cables, and there is always also the idea to reuse the cable. Is it possible to, for a bigger project, for example, measure different lines installed in the field and get back this data into the emulator to simulate such real cables installed since many years, to be sure before they switch over, for example, from hard communication to APL with single PA Ethernet, that it works? Is it possible too?
Well, Telebyte makes the lab equipment, but if you could qualify some of the cables with some field testers, if you could come up with different parameters. Our cable emulator is based on the standard cable model, so we can't simulate every cable because it's a fixed hardware design. But what we could try to do is work with the customer to tune what their cable parameters are in terms of insertion loss or return loss, or and try to map something, a length to use on our cable emulator. And then we could add noise if we're measuring noise on that cable environment or crosstalk. And so we can try to reproduce a condition, but we'd have to tune the specific, because we won't be able to match that cable identically. Our box is fixed for the standard cable models.
Yeah, okay. In this case, it might be also better to qualify the cable with a cable test equipment in the field, and
well, we can try to match some of those characteristics by setting attenuation or DC resistance, because we can vary the DC resistance to see if you can supply stable power. So you can do some testing in the lab up front to see how the devices work, maybe put into a similar environment.
Okay. Here's some more questions. So thanks so far. Does the system support also remote testing? So you have it in your lab, and over the weekend or you can set up tests from outside. I guess this is the meaning of this question.
Yes. So all of the Telebyte equipment has either Ethernet ports. You can put them on your lab network, behind a VPN, and your test setup. You can talk to the computer, and we have customers logging in and running tests 24/7. So the test setup is, as long as we have tests in our universal test setup approach, you have one setup, and you should be able to test those devices over the complete range of tests without changing cables. So you can basically run a software script or manually, remotely access equipment and do some manual testing as well if you wanted to change noises or something like that, or change cable lengths manually. But generally our customers will do set up their test cases and then run automated scripts. But yes, remote access is supported, especially we've seen now during the COVID pandemic. We've had customers request Telebyte to have remote access to the entire test bed to continue their testing remotely.
Very good. Yeah, it's really a lot of interest. So we are running out of time, but I have one last question for you, and it shows also that there's a lot of interest in your topic here. What type of training do you need to run this conformance test equipment?
Well, definitely you have to be familiar with the 10-base T1L technology, and manual testing requires skilled engineers or technicians to run it. Telebyte is trying to support this with an automated universal approach so that any technician could run these tests and then produce accurate test results. So we're trying to simplify the connection of all the, supporting power and data, and then having instruments that are protected from that power and data, but having one setup where you can run the test. So we're trying to reduce the complexity of the testing and have a repeatable setup. So we will Telebyte definitely provides training on the different tests and our setup, and but with some training you should be able to run the complete test setups and produce accurate results.
Yeah, very good. Yeah. So I guess there's some more interest, but we're running over the hour, and I see some of our audience is moving, because I guess some have another meeting again. So thanks so much for all these details. This super interesting presentation today. To all of you who get not the answer for the question, we will manage it that you get it. And if you have interest to these devices or to more details, you will easily find the website from our colleagues from Telebyte. You can go in direct contact, especially for such a test equipment. It's always also good to have the right and direct contact to the colleagues. So use this. And once again, I want to invite you to one of our next coffee breaks. So we will have always interesting topics, and hopefully we will see us again. and enjoy your day. And thanks a lot to you, David. Yeah.
Thank you very much, Matthias. Have a good evening.
Yeah, have a good day.
Thank you.
For us, Europe, good evening. Thanks. And it was a big pleasure to have you here, and it was super interesting. Yeah. Thanks to you, and thanks to all who have listened today. See you soon. Bye-bye.
Thank you. Bye-bye.